Welcome everyone to section number 8. This is related rates. As you can see, I've titled this video Round 1, Fight. And likewise in the second video, it's Round 2. The claim is this is a difficult topic. This is going to be basically your applications of implicit differentiation into real world problems. And if you ask your random math instructor or just someone who's taken calculus before, what are the big topics of calculus, everyone's going to list related rates. This is one of the core objectives in calculus, is to be able to solve related rate questions. So this is an important topic. So it's good we have a couple videos to really get this down well. Okay, so what do related rate questions look like? Well, they will feel very different, right? And as you're doing these things, again, you're going to use different equations and stuff like this, but there's kind of a general underlying technique to solving these related rate problems. So this is the general technique. So the first step is that you want to relate given quantities with an equation. Second of all, you want to differentiate this equation. Differentiate the equation using implicit differentiation. And you're going to see we're going to have a lot of chain rules here. And then finally, you're going to solve for some rate of change, aka a derivative. So this is the general underlying technique to all these related rates questions. So this first one is a little bit daunting, right? Relate the given quantities with an equation. Well, what equation to use, right? And the claim is we need to know and kind of remember these geometric and trig equations or formulas that we've encountered in our previous math classes. So for instance, for circles, you have circumference, right, is pi times the diameter. Diameter is 2 times radius. Area is pi r squared. For triangles, you should know something about the area of a triangle, 1/2 base times height. If you have a right triangle, then you have something like Pythagorean Theorem. Sine is opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent, right? And the list goes on for rectangles, for spheres, for cones, for cylinders, right? These are the equations that we're kind of expected to know that we'll be using in a lot of these problems. Okay, and then which one do we use? Well, that'll come down to the particular problem. So let's go ahead and see an example here in this video. We have a sphere is growing. Its volume is increasing at a constant rate of 10 cubic inches per second. R of t, V of t, and S of t are radius, volume, and surface area of the sphere at a specific time. Right? Those are changing with time, though. And it says if R of 1 is equal to 2, so that is the radius at time 1 second in, is equal to 2, then I want to compute these things, R prime of 1 and S prime of 1. So this is a good kind of warm-up problem. We'll do more difficult ones later on, but this is good to kind of start getting the juices flowing. Okay, the big thing here, well, first of all, maybe if I look at this, R prime of 1, we want to, first step, relate given quantities with an equation. So the given quantity, and as I kind of skim through here, well, I have something about the radius itself. The radius at time 1 is equal to 2. And then I also have that the volume is increasing at a constant rate of 10 cubic inches per second. So this is talking about a rate of change for volume, right? How is it increasing? Well, it's increasing at 10 cubic inches for every second. So rate of change, remember, this is one of those fancy words for a derivative, right? So this is telling me something about the derivative. So this is volume. The derivative of volume is equal to 10. Or if you wanted to be a little bit more precise, right, this is kind of shorthand, right? This is V prime of t is equal to 10. All right, so the volume is increasing at this constant rate, 10 cubic inches per second. Okay, so the things that we have, right, radius and volume, notice all of this is talking about a sphere, so I need to choose an equation that relates together the radius and the volume of a sphere. And so I can go back here onto my last page, and I can see for spheres, we have volume is equal to 4/3 pi r cubed, right? And so this is a way to relate together volume and radius. All right, so I'm going to go ahead and use this. Volume is equal to 4/3 pi r cubed. And now the big thing here is that the volume and the radius, they're changing with time. So this is not a constant sphere, right? As time changes, the sphere is growing, right? So really, to be more accurate, it'd be nice to say v of t, the volume at time t, is equal to 4/3 pi, right? These are all constants here, but that radius is growing with time as well. So maybe r of t cubed. Okay, so now we have officially completed that first step, right? Getting an equation that relates together the given quantities. The second step is to differentiate this equation using implicit differentiation in the chain rule. And that kind of makes sense because, again, I want r prime of 1. Well, I don't see any r primes in this equation, but if I take the derivative, I will, right? So if I take the derivative of this, on the left-hand side, well, v is going to become v prime, right? The derivative of the volume. And then let's see, if I take the derivative here, well, this 4/3 pi is all a constant. And then, okay, the 3 is going to come down, and I'm going to have r of t raised to the second power, right? So this is now the chain rule. The outer function is stuff's being raised to the third power. So the 3 comes down, reduce my power by 1. And then the chain rule says multiply by the derivative of the inside. And that's why I had that extra phrase here, is that you're going to use implicit differentiation and the chain rule, right? So I took the derivative on both sides of the equation. You got to make sure you use that chain rule there. All right, now let's go ahead and see what we have. Well, first of all, we notice that v prime of t is equal to 10, so I could go ahead and substitute that in there. Let's go ahead and do that. So this is going to be 10. Notice I have a little bit of cancellation, 3 on top, 3 on bottom, so this is going to be 4 pi r of t squared times r prime of t. And the last bit here is that I want to solve for r prime of 1. So maybe everywhere that I see a t here, right, these are general formulas with t's in them, well, I want to plug in 1 instead of t. So I'm going to go ahead and maybe start rearranging a little bit. So let's see, this is going to be r of 1 squared times r prime of 1. Again, my goal is to solve for r prime of 1. We have r of 1 is equal to 2. So the radius at time 1 is equal to 2. So this is going to be 2. So 10 is equal to 4 pi, and then 2 squared is going to be 4 r prime of 1. So let's see, we're going to have 16 is equal to 16, sorry, 10 is equal to 16 pi, getting ahead of myself a little bit, r prime of 1. And so this is going to be 10 over 16 pi is equal to r prime of 1. We can do a little bit of simplification. And so we're going to have 5/8 pi. And then also, anytime you have one of these real world problems where you have units, we should always consider the unit here. So this was 10 cubic inches per second. So it seems like the unit of length is inches and the unit of time is seconds. So this again is asking, how is the radius growing, right? So what is the rate of change for a radius? Well, radius is going to have length of length of inches, right? And how is it changing? Well, this is going to be inches per second. So that is my r prime of 1 with my correct units. Okay, so that is the first problem. Let's do a similar problem here for finding s prime of 1. And I'd like you to go ahead and pause the video and try this one on your own. The claim is it's related to this up here. You still have how is the volume changing. In fact, you actually have now how is the radius changing. You may want to use that. And then the question is, how is the surface area changing at time 1, right? S of t was the surface area of the sphere at time 1. So again, pause the video, try to get as far as you can, and then we'll go over the solutions together. All right, and so for this one, I went ahead and used the surface area equation, right? Which makes a lot of sense. So again, if I zoom back to the previous page and I go for spheres, this went too far, we have surface area, in this case we were denoting it with S, is 4 pi r squared. So that's my equation that I started with. I then went ahead and recognized that, hey, this surface area and this radius, they're changing with time. So technically they are functions of time. And so I went ahead and used my function notation, S of t, R of t. Now I went ahead and I took the derivative. Notice we have 4 pi along for the ride here. The 2 comes down. This is technically raised to the first power. And then we have r prime of t because of the good old chain rule. Then you plug in 1 everywhere you see a t because, again, our goal is to figure out s prime of 1. How is the surface area changing 1 second into this? And so I plugged in 1 everywhere I saw a t. Well, notice this 2 and this 4 made a total of 8 pi. R1 was 2, according to up here, right? R of 1 is equal to 2. And R prime of 1, well, we solved that in the previous version, right? The previous part. So this is 5 over 8 pi. And so the 8 pi's kind of cancel here, and you get 2 times 5 is equal to 10. Again, I want to remember my units in this case. So my units for surface area are going to be square inches. And then this is the derivative, right? How is it changing? So we know that the derivative is going to have units for surface area and then divided by the units of the independent variable time in this case. So this is going to be square inches per second. So there we go. There's my final answer for this problem. All right, I have one more example for you, and this is a classic one. You know, this shows up kind of everywhere. You're definitely going to see a homework problem like this one. We have a ladder, right? A 13-foot ladder leaning against the wall, and it's sliding down, right? It's slipping. The top of the ladder is moving downwards to the wall at 3 feet per second, and the question is, how fast is the bottom of the ladder moving away from the wall when the bottom is 5? So reading through this, right, this maybe is a little bit more daunting because it hasn't even specified a shape, right, of kind of where should this equation come from. But when I start to look at this a little bit, right, for instance, it says that this ladder is moving downwards along the wall at 3 feet per second. So that means that this point right here is going down, and that's at 3 feet per second. So that's somehow telling you how this length, maybe I'll use a different color here, this length right here is changing. It's changing at 3 feet per second. And the question is, right, how is the bottom moving away from the wall? As you can kind of imagine then, that this point would be sliding out at a particular instant when the bottom is 5 feet from the base of the wall. So it's wondering, how is this changing? Or better yet, how is this length increasing at a particular instant, right? Again, when the bottom is 5 feet away from the base of the wall. And so now you can kind of see that, yeah, I've drawn this triangle thing. So maybe this is actually a triangle question. And I mean, assuming that this wall is actually straight up and down, this is even a right triangle. And you're relating together this 13, this orange side, and this green side. So you're relating together the sides of a right triangle. And so looking back on my formulas that I have, right, my triangle, well, it's not really something to do with area, sine and cosine and tangent, right? These all have angles. I don't really have any angle information. But here we have the good old Pythagorean Theorem, right? A squared plus b squared equals the hypotenuse squared, c squared, right? So I think that one would be a good one to relate together the sides of this triangle. So let me go ahead and note these with some names here. I'm going to call this one y of t, right? So this is the height of this ladder at time t. And then this one I'm going to go ahead and call x of t. Right? So this is the distance away from the wall that the base of the ladder is at time t. And then I would have a formula that relates these together, right? So I have x of t squared plus y of t squared is equal to 13 squared. And right, the ladder is not changing in length. It's not shrinking or growing or anything like this. So it's just a constant 13. So now let's go ahead and take some of this information that we're given in sentences and turn these into mathematical equations with our new notation. So for instance, the fact that the ladder is moving downwards along the wall at 3 feet per second, this is telling you how this y value is changing, right? So it's a rate of change for that y value, aka it's going to be talking about the derivative, right? Derivatives are rates of change. And so it says that it's going down by 3 feet per second. So we'd probably write -3 in this case, because again, it's shrinking, it's going down, it's getting closer to 0 here, and it's going at a rate of 3 feet per second. Now the thing that we want to know is, how is this x value changing, right? The question is, how fast is the bottom of the ladder moving away? So this is asking, how is this x value changing? Again, it's a rate of change. So in order to answer this question, we want to solve for what is x prime, at a particular instant, right, before we had at time 1, right, up here it was at time 1. In this case, right, we don't know the exact time. It says, well, when the bottom is 5 feet from the base of the wall. So it doesn't say at time 2 or at time 3, but at some time when the base is, right, 5 feet away from the wall. So, all right, so I need to choose a time. Well, here I'm going to go ahead and I'm going to use A. Right, so I don't know what that time is. It might be 1, it might be 2, it might be something, but I want to know, how is that changing, right? How fast is the bottom of the ladder moving away from the wall? How is this changing? So that's how I'm going to answer this question. When the the bottom of the ladder is 5 feet from the base of the wall. So the information says that x of A at this special time, this x value should. And again, that A value could be 1, it could be 2, it could be, it could be any time. It doesn't specify what time it's at, so I'm just using A as kind of a placeholder almost, right? If you're in a lot of physics class, you may use like T sub 1 or T sub 0 or something like this to denote a specific time. All right, so we were able to code all this information that we're given and the information that we want, right? So again, we want, how is this ladder moving away from the wall? So x prime of A. Well, now we move on to step 2, right? We go ahead and differentiate this equation. So again, the 2 comes down and we have x of t raised to the first power times, right, thanks to the chain rule, we have x prime of t. So this is a derivative with respect to time. Next up, 2y of t, technically raised to the first power here, times y prime of t. And the derivative of 13 squared, and this is kind of maybe a little misleading the way that I have it written, but right, 13 squared is the same thing as 169, right? So the big thing here is that this is a constant, so this is equal to 0. One common mistake that I see is people try to do the power rule to this, right? But this is not x squared, it's 13 squared, so it's a constant and it has a derivative of 0. Okay. Now, one thing that we could do is go ahead and divide through by 2 on both sides. So I'm going to have x of t times x prime of t plus y of t times y prime of t is equal to 0. And in fact, we know y prime of t is equal to negative 3. So let me go ahead and erase this really quick. And I'm going to go ahead and put negative 3 there. And now remember my goal. My goal is to solve for x prime of A. Right, so at a specific time A. So now I'm going to go ahead and place in, everywhere I see a t, I'm going to put an A. So this is going to be x of A times x prime of A plus y of A times negative 3 is equal to 0. And I know this x of A, right, so this is again this length, how far is the ladder away from the wall at this particular instant, is supposed to be 5 feet. So I'm going to go ahead and erase this. And I can make this 5 feet. Okay, so I'm pretty close. Remember, my goal is to solve for x prime of A. The only thing that's really keeping me from doing this is that I have this extra variable here, this y of A. If I could somehow get rid of that, then I could just move everything to the other side, and I would get x prime of A. So I need what y of A is. So what is the height of this ladder at this particular instance? So I'm going to go ahead and draw another one of these triangles here. So at that particular instant of time, right, at time A, right, I know that the ladder is 13 feet long, and I know that x of A at that particular time is 5. And the question is, what is y of A? What is the height this ladder reaches at this particular instant? And so we can see, in order to solve this, I can use the Pythagorean Theorem again. So this will say that 5 squared plus y of A squared is equal to 13 squared, which again, maybe I should just go ahead and write 169. Let's go ahead and move this over, and I'm going to get y of A is squared is equal to 144. And then if I take the square root on both sides, I'm going to get y of A is equal to technically plus or minus 12. But remember, this is a height, right? So it's going to have a positive value. And therefore, we can kind of exclude this negative one, and it's just going to be positive 12. So y of A in this case is positive 12. And so now I can go ahead and substitute that in up here. So I'll have 5 x prime of A's plus 12 times negative 3 is equal to 0. that's going to be negative 36. So I'll have 5x prime of a's is equal to 36, right? Once I add that over to the other side, and then I just divide and I get x prime of a is 36 fifths. So there we did it. I solved how fast is the bottom of the ladder moving away from the wall at this particular instant in time. Let's go ahead and add our units here. So this is going to be, again, how is the x value changing? Well, x value is going to have length feet, and it's changing, right, units of seconds here. So this is going to be feet per second. So there is my final answer, 36 over 5 feet per second. All right, that is our first video. It only gets more complicated from here, so we're going to do a few more complicated problems here. So there is my final answer, 36 over 5 feet per second. And that's it for our first video. Go ahead and take a break. I know that some of these problems, right, they're difficult, but get right back in there, watch the second video, and start trying some of your homework problems. I'll see you guys next time.